In this first and very basic assignment of probability question, we just have a sample of coins from a bag. We would like to assign a probability to drawing a nickel. So the probability of drawing a nickel is simply the number of nickels that we see in the sample divided by the total possible numbers of coins that we could draw, total possibilities. To do that, we need to know the total. See how many were involved. There were 23 quarters, 29 dimes, 17 nickels, and 38 pennies, for a total of 107. Of those, 17 were nickels. So 17 and 107 is 0.1589 to 4 decimal places. To answer the question where we are happy with either a quarter or a dime, now we have a little bit of a compound event, the probability of a quarter or a dime, Q for quarter, D for dime. That's the probability of a quarter plus the probability of a dime. Now that's the probability notation. Sometimes we just approach it as straightforward, like how many ways can we go? Well, we would like to have. We would be happy with 23 of the quarters or any one of the 29 dimes. So that's 23 quarters and 29 dimes. Either one of them would make us happy out of a total of 107 possibilities. So 23 and 29 together are 52. Divided by 107 possible options, 52 ways to be happy out of 107 is a probability of 0.48598. It's an interesting rounding situation. The 9 looks next door to the 8. The 8 is big, so the 9 overflows into the 5's place. So rounded to 4 decimal places, this is 0.4860. The next question uses the deck of cards here that I have for us just for reference. First, we notice that there is one card drawn only, so we only have a single event, and we want the probability of drawing an ace. The probability of getting an ace is simply the number of aces divided by the total possibilities. Again, very basic assignment of probabilities here. We'll use this a bunch going forward when the events become more complicated. There are 4 aces here, if we count them, and 52 total cards. So 4 divided by 52 is a probability of 0.0769. The next question is a little bit more interesting, the probability that we do not draw a 2. We can use the complement rule for this, the probability of a 2 complement. So the event is draw a 2, but we don't want that to happen. With the complement rule, that's 1 minus the probability of drawing a 2. Now, without using the complement rule, we could just count all of the cards that are here, those aces plus all these guys together are not 2. So we could count those cards and put them out of 52, or we can simply be faster, just count the 2's. There are only 4 2's, so we will not have a 2 if we don't have one of those 4 2's. If we have 1 minus 4 out of 52, that's a little bit faster just to count the 4 2's rather than every card that is not a 2. So 1 minus 4 out of 52 is 0.92308, or remember to 4 decimal places, so 0.9231. Again, next example is very easy if we have a good sample space to work from. A standard pair of dice are rolled. What's the probability of rolling a sum of 5? We're happy with a sum of 5, so it's very helpful to have this sample space, possible outcomes for rolling 2 die. This guy adds up to 5, this guy adds up to 5, this guy does, and that guy does. There are no other ways to roll 2 die and get a 5. If you don't have the sample space, you start thinking, how can I make a 5? I could have a 1 and a 4, have a 2 and a 3, a 2 and a 3 again, or another 1 and a 4. Those are the only ways to do it. So the probability of getting a sum of 5 is simply these 4 opportunities to get a 5 divided by the total sample space, the size of the possible ways to roll. There are 6 ways in the rows and 6 in the column, so 6 by 6 means 36 possible options. If you don't believe me, count them. 4 out of 36 is 1 out of 9, or 0.1111 to 4 decimal places.